Good afternoon, everyone. So for our PCS seminar today, we have Dr. Clemens Gneiting speaking. He did his PhD in Munich in 2010. He's held postdoctoral positions at Max Planck Institute for Complex Systems in Dresden and the University of Freiburg. Since 2016, he's been a research scientist at RIKEN in Japan. His research interests are broadly in open quantum systems and more recently in quantum machine learning. And he's going to be talking to us about eigenstate extraction using neural network tomography.
Great. Thank you very much for the introduction, Daniel, and also thank you for the invitation to give this presentation here, which is, of course, great. Now, you see this picture, maybe, yeah. This is actually a recent picture from RIKEN campus this year, March, but actually, this is about the time when I last saw RIKEN because RIKEN has been in shutdown for 2 months now. So let's hope I can return soon. Now, as Daniel mentioned, my main research topics are more on open quantum systems or disordered quantum systems, also topological quantum systems. But quite some while ago, we also started to be to get interested in machine learning, and now here I want to present some results, well, quite recent results that we obtained in that direction. Now the topic this talk focuses on or centers on is about tomography. Now tomography, of course, we know this is important. We have experiments. We want to know what's the actual state that's produced in experiments. And nowadays, in the age of quantum technologies, where quantum devices get more and more complex, of course, this that only increases in relevance. Yeah. But then, at the same time, we also know that tomography is very demanding, both on the experimental side and on the computational side. I mean, because we have a huge requirements in measurements and huge computational costs. Yeah, but then on the other hand, we know machine learning is actually, like, by definition, exactly designed to deal with such situations where we have to handle big data and have complex computations. And therefore, this seems like a good match, yeah. And actually, there have also been works on applying machine learning to tomography, but they mostly focused on applying tomography to pure state. So that's pure state tomography. And in this project, we aimed at generalizing to full-fledged mixed state tomography. And the idea behind this, like leveraging the pure state tomography for mixed state tomography by eigenstate extraction. So this is the outline of my talk. Now, in the first part, I will briefly recapitulate why actually tomography, what's the challenge with tomography, what's the idea and the challenge. Then in the second part, I will give a more general introduction into machine learning, and in particular into neural networks. Then in the third part, I will explain how neural networks can actually be used in order to describe quantum states, or more specifically pure quantum states, and also how they can be used for pure state tomography. And then in the last part, I will finally explain our idea of using this neural network pure state tomography to apply it for full-fledged mixed state tomography. Okay, let's start by looking into quantum state tomography. Let's recapitulate a few facts. Now, the simplest system we can think of is a single qubit, and we all know in the case of single qubit, we can describe the quantum state by the Bloch vector, which is 3 real numbers. And accordingly, if we measure the state in the Pauli basis, like we have 4 Pauli matrices, then we can, from the expectation values, basically infer the exact quantum state, the underlying quantum state. Now the challenge starts that if we go to large numbers of qubits, because then the number of required, or the measurements, or the number of possible Pauli measurements, so to speak, scales exponentially in the number of qubits. And this then, of course, rapidly gets prohibitive in experiments. Oh, sorry. And at the same time, we also know that the expectation values are noisy, and therefore we to take this into account, we have to estimate make a best guess for the quantum state that describes the measurements, and this is usually, or can be done with a maximum likelihood estimation, and this is again very costly in terms of computational costs and time consuming. And just to give you an idea of what this can mean, let's look at this prominent example. Like some time ago, the Innsbruck group on trapped ions, they did a tomography experiment. They had an 8-qubit state and generated a W state. And in order to verify the state, so they did the full tomography, they did all the Pauli measurements, and then the post-processing of the measurement data took them an entire week to obtain the state estimation. Now, of course, there are smart ideas in how this can be sped up, both on the experimental side and on the computational side. For example, there's the idea of compressed sensing, which basically tells us that we can, with very high probability, obtain a good state estimation also with a substantially reduced amount of measurement data. Or another example would be different reconstruction methods, for example, linear regression, which then mitigates, so to speak, the computational cost. But these approaches also have their issues, and of course they also quickly hit a wall, get prohibitive. Yeah, and maybe I should have mentioned.
Clemens,
yes?
Sorry, we have a question by
Yes.
Igor.
I should have mentioned the questions. Please interrupt at any time and ask any time. Yeah, that's perfectly fine. Now, I would like to see the questioner, but I'm not sure if I can do that. But never mind. Please, please ask. Yes.
If you insist. Hello, Clemens. So I was wondering about this 8-qubit post-processing. So can you give us any idea about why it's so long? Because 4 to the power 8 is not an astronomically large number, right? It's like 50,000. So why would it take so long? What kind of mathematical problems, algorithmical problems are solved to get this maximum likelihood estimation?
Of course, I mean, I think one thing we have to take into account that this experiment was done 15 years ago. So probably the computers back then weren't that fast, but still, I mean, they write it explicitly in their paper that it took them 1 week. And of course, I mean, it's a huge, it's a high dimensional parameter space, and the maximum likelihood estimation is just in itself costly, because we have to find the quantum state that, so to speak, minimizes or maximizes the likelihood, but at the same time needs to satisfy the constraints that it's like a well-defined quantum state, in the sense like trace 1 and positive and so on. Yeah, so
I see. So it's an optimization problem in a multidimensional space.
Exactly, and I mean, 8 qubits. I agree, 8 qubits is not that big. Yeah, so back then it took them 1 week because they wanted, so to speak, to get the highest quality possible, so to speak. They didn't want to make any, so to speak, give up anything. Yeah. But of course, you can easily imagine if nowadays, like the present day machines that you see, that like Google or IBM building, they easily reach numbers of 50 qubits. And I mean, you quickly hit the wall, yeah.
I see. Thank you.
Thank you for the question. Yes?
Clemens, hi, nice to see you. And let me
Hi.
add on this. Can you maybe still elaborate once again why this measurement becomes an optimization problem? So just for pedestrians like me. Say I have, let's take the simplest example of a single qubit even, which you have here. So
Yes.
so now I measure what? I measure the expectation values of the sigmas, and then what? Then why do I have to solve an optimization problem? Can you?
Now, I mean, let's assume, I mean, we don't know rho, so we don't know the Bloch vector R, yeah? So if we want to find the R, and now let's assume we measure the 3 Pauli matrices. I mean, in the case of single qubit, we don't really need the sigma naught, yeah? We measure the 3 Pauli matrices, and in the ideal case, we get exact expectation values, and from then we can completely infer on the 3 components of the Bloch vector. But now, and there's everything is consistent in the ideal case, yeah. But
so that is not an optimization. That's just a straight map, right?
Yeah, not yet, yeah. But now imagine you go to larger number of qubits, and then if you do measure all the Pauli matrices, then your information will be overcomplete, and you will have, in addition, you will have noise on the expectation values, so that you cannot expect that you will find an actual well-defined quantum state which satisfies all expectation values simultaneously, so to speak, yeah. And then that's where this maximum likelihood estimation sets in. You need to find a mixed quantum state, so to speak, which approximates all the expectation values, so to speak, in an optimal way.
But what happens if I try to cheat and I just measure as many observables which I need to, so to say, have a one-to-one mapping, so that things are not overdetermined? What happens there? I guess something goes wrong, but
I guess it's simply not so easy to find such a set of measurements that, so to speak, or it's just not what you can do experimentally. I mean, experimentally you just measure. You measure local observables, yeah, and then you will necessarily have redundancy, yeah.
Right. Okay. Thank you.
Thank you for the questions. Can I continue?
Oh, yes. Please.
Okay. Okay. Now, in view of this, these challenges of that we face in quantum state tomography, and also knowing that machine learning is basically there to like help us with such problems, we can of course ask, can we use machine learning for quantum state tomography? And this will be the topic of this talk, of course. But first, let me give a brief, more general introduction into machine learning, or more specifically into artificial neural networks, which is one of the branches in machine learning. I mean, machine learning is not just artificial neural networks, but actually they have been among the most successful ones in the last, I mean, since this machine learning boom started in the last decade or so. And the underlying idea is actually in principle very simple, yeah. I mean, a single artificial neuron, what it does is it takes inputs and weights them by their significance, and then just adds them up, yeah, the inputs. And then if this sum, so to speak, exceeds a certain threshold value, then we say that the neuron fires. If not, it does not fire, yeah. And if it fires or not, this threshold, so to speak, function, this is called the activation function. And this is importantly, this is a nonlinear function. So that the artificial neural networks or artificial neurons, they, so to speak, is an important property or characteristic is that they combine linear processing and nonlinear processing. Yeah, that gives them, so to speak, a lot of power. Now, the choice of the activation function is not unique. There are many possible choices. In principle, I mean, the only necessary, okay, now there's also the linear one for simple cases, but usually what you want it to be is that it's nonlinear, but then you really have a broad spectrum of choices. Among the more popular ones are the more broadly used ones are, for example, the sigmoid, which is also one of the oldest ones, or another one which is not displayed but which has been very successful also is the ReLU, the rectified linear unit, which is basically like half constant, half linearly increasing activation function. This has been, in particular, been very successful in image recognition. Now, what the artificial neuron does, basically, more abstractly speaking, is it defines a decision boundary in the input space. Yeah? Of course, a single artificial neuron itself, it only generates a single linear decision boundary in the input space, so there's not so much to do with it. But of course, we know these neural networks have been used for very complex tasks like image recognition, for example, like distinguishing pictures of cats and dogs, classifying them correctly. And obviously, if we just have the simplest case of a single input layer and a single output layer, nothing in between, then this is just a bunch of, then this produces just a bunch of independent linear decision boundaries. There's not much we can do with that. So the next most straightforward generalization beyond that, so to speak, is then to add a single hidden layer in between the input layer and the output layer. And this then is already quite powerful because it can be proven that in this case, already we can reproduce arbitrary nonlinear decision boundaries. So actually, one can prove that any continuous function can be approximated this way. Yeah, of course, only if we allow for an arbitrary number of hidden nodes. Yeah. Now this is
sorry, just a quick question.
Yes.
On that again. So you show here a hidden layer which has a higher dimension than the input and output layers.
Yes.
But it probably can also be have a smaller one. So what's the difference between them?
You mean the difference in the numbers, or?
Well, you show here that a hidden layer has an increased dimensionality. Okay, that's probably one class of problems which you might try to approach, but you can as well also choose hidden layers which have smaller dimensions.
Of course, yeah. In principle, you can choose any number of hidden.
Yeah, well, what is then the principal difference? Well, where are we going? Naively, bigger or smaller?
Naively speaking, the larger the number of hidden nodes, the more powerful is the neural network. But this is that's only true in naive thinking, because in practical terms, what you have to take into account is always like how easily can you train the network, yeah, and then of course usually, and this is where a lot of heuristics enters the game. People play a lot around between like the dimension of the hidden layers, just to find the optimal size between expressibility of the network and trainability, where it still remains. Because if you make it too powerful, then the network easily gets prone to overfitting. Yeah, if you make the number of hidden nodes too small, then it's too coarse. Yeah, you won't be able to create a decision that the details in the precision in the decision boundary that you require if you want to do some classification, say. Yeah. So there's no strict rule about how to choose the number of hidden nodes, and it's completely unconnected from the dimension of the input layer or the output layer. And also input layer and output layer in general don't have to match dimensions. Yeah, they can also be different. For the input layer, for example, you can think of as the pixel data from images, yeah, and the output layer, for example, you can think of like giving you classification information, for example, cat, dog, cow, horse, whatsoever, yeah, but as much as you want to classify, yeah? As many different categories or classes you want to classify.
Okay, thank you.
Thank you. Okay, now we have the network, like the basic structure, but still we need somehow to find a way how to find the optimal choices of the network weights, yeah. So we need to train the network in the jargon, yeah. And for this, usually in the paradigm of supervised learning, we take we require that we possess, so to speak, a bunch of training data, which is which consists of input points or vectors and the corresponding correct output vectors. Yeah, so this is called supervised because we for a certain number of inputs we know the correct outcomes, the correct outputs. And then from the training data, we can construct the cost function, which basically simply measures the difference between the network prediction and the correct output. Yeah. And then basically it just turns into an optimization problem. We can, in small steps, improve the network parameters towards minimizing the cost function. Yeah, but we have to be careful not to get trapped into a local minimum or into a minimum which corresponds to overfitting. Yeah, but this is now more details that I don't want to enter into too much now. Also because this is not the issue so much in this tomography business that we are talking about here. Okay, that's the basic idea, and ideally, if we have a well-trained network, then even if we get, if we input, so to speak, input vectors where we don't know the correct answer, which are not labeled the correct output, the network is then able to predict the correct output. So if say we give as an input a picture of a cat which has not been part of the training data, and if the training was successful, then the network can successfully or correctly classify this as a cat. And this is then also what's called generalization. Now, of course, these shallow networks are not the end of the story. There have been like the really powerful and successful network architectures that have caused this progress in the last decade or so, have been, for example, like more complicated architectures like deep neural networks where we have many hidden layers, or convolutional neural networks. This is where we basically exploit some sort of translational invariance in the input data. Or recurrent neural networks is, sloppy speaking, some temporal invariance where we can share network parameters efficiently. And of course, we can also have combinations thereof. Yeah, and then overall, this turns out to become a very powerful family or ansatz family to represent like the many real world decision boundaries, so to speak. Yeah. Okay. Very briefly, I mean, there have, of course, been many reasons why neural networks have become so successful in the last decade. One of the reasons, or one of the prominent reasons, is of course that because of the internet and because of digitalization, we now have all the massive training data, the big data required to train the networks. And on the hardware side, for example, a lot of progress comes from using GPUs instead of CPUs. Yeah. And as I already mentioned, one of the like pillars of success of neural networks has been image recognition. And one of the milestones here was, for example, when the first time when the artificial neural network architecture actually outperformed humans in image recognition. So this was in 2015. And now, more recently, in the last years, physicists have also started thinking about using machine learning for beneficially in physics. For example, machine learning has successfully been used to classify spin models, which thermodynamic phases they are in, or to detect entanglement in mixed states. Also, an application is to correctly find the topological invariance in the input data, or more ambitiously, even people have tried to use the neural networks or machine learning neural networks specifically to in some sort predict physical laws, for example, like derive Kepler's laws from some planetary motional data. Yeah. Okay, now the kind of the flavor of neural network that I want to talk now, or I want to focus on in the remainder of my talk, is actually a slightly different flavor. It's called restricted Boltzmann machines. It's also, I mean, these models are actually all very old already. Yeah? It's only they have been so successful now in the last decade for the reasons I just mentioned. Yeah, but they were conceived a long time ago. Here also in the restricted Boltzmann machine, also we have, the idea is we have two layers, the visible layer and the hidden layer. But here we think of this, it's a physics-inspired ansatz. So we think of this as a spin model, and we associate it, so we have the couplings, the weights are now, we think of the weights as of the couplings, and then we associate with this model an energy function, and then we can thermodynamically thinking associate with the model a Boltzmann distribution. Now this is a probability distribution, and the purpose of the restricted Boltzmann machine is to approximate probability distributions, and now the target distribution that it's meant to approximate, so to speak, is the marginal probability distribution for the visible spins. Yeah. And now the big advantage of one of the appealing features of the restricted Boltzmann machine, or RBM, is that we can efficiently generate sampling of our probability distribution just by Gibbs sampling, by jumping back and forth many times between the visible layer and the hidden layer. We can generate samples of drawn according to the probability distributions, and importantly, to get these samples, we do not have to know the partition function of the probability. So the probability distribution does not have to be normalized. Yeah, because this is important, because in if the model is very large, so if we want to have a very high dimensional variable space, parameter space, then this again becomes computationally prohibitive.
Sorry, Clemens, can I quickly ask you a question? So looking at these restricted Boltzmann machines, what is the difference between these and standard Monte Carlo simulations? Is there some big advantage you get out of these Boltzmann, because you do a similar sampling with Boltzmann weights even there?
Probably it's I mean, there are many similarities, of course. Yeah, I hear that. I think here the idea is that, or the philosophy is more from this neural network way of thinking. Yeah, that we have the visible layer and the hidden layer, and what I forgot to mention is the reason why it's called restricted Boltzmann machine is because we do not allow interactions between the spins within one layer. So we have only the interlayer connections. And in principle, we can, sloppily speaking, unravel this also in some sense into a feed-forward neural network just by, instead of going back and forth, we just concatenate the layers, yeah?
Yeah, exactly. Mm-hmm.
And then we are closer to this original artificial neural network way of thinking, yeah? I think, yeah, but of course, because this is a physics-inspired model, probably it's there are many similarities, yeah, to other existing Monte Carlo approaches. Yeah? And the sampling certainly is like a common trait, yeah?
Mm-hmm. I see. Okay, thank you.
Okay, now the RBM is basically still very general. It can be used to approximate, or it is being used to approximate arbitrary, in principle, arbitrary probability distributions, yeah, not restricted to physics applications. But now we want to understand how they can actually be used to capture actual quantum states, yeah. In principle, the idea is pretty straightforward because, you know, I mean, at least in the case of pure states, we know the wave function itself, it already adheres to some sort of probability interpretation. I mean, it's a probability amplitude, yeah, but still, it's very straightforward to associate, so to speak, a probability distribution to the amplitude of wave function we can associate with a probability distribution. And this probability distribution we want to describe by a restricted Boltzmann machine. But to get the most general wave functions, we of course also have to include the possibility of phases. And then we need a second network, say, to describe the phase or to capture the phase information. This can again be an RBM, or it can just be a feed-forward neural network, because here it's not so crucial that it describes a probability distribution. Yeah. Now, this ansatz, or the combining, so to speak, or applying the RBM to the description of pure quantum states, this has been put forward in 2017 by Kaleo and Troyer. And back then what they showed is that this ansatz is basically very powerful, or can be very powerful in capturing complex and highly entangled quantum states, yeah, of, for example, high-dimensional spin models with large numbers of spins. And one conceptually interesting aspect here, of course, or what distinguishes this ansatz as compared to other ansatzes, like, for example, say matrix product states, is that here we do not have to impose like locality constraints or constraints on the dimension of the system. Yeah, in principle, it's very generic, but of course, it's still an ansatz, and it also has its limitations. They're just maybe less obvious. Yeah. Now, the problem that Kaleo and Troyer back then applied it to was like finding the, or approximating the ground state of a Hamiltonian, for example, the transverse Ising Hamiltonian of a spin chain. And they could achieve this successfully to a very good accuracy, for example, for spin chains of up to 80 spins with a choice of alpha equals to 4. Now, this alpha basically describes the ratio of number of hidden spins versus visible spins. So here, alpha equals to 4 means the number of hidden spins was 4 times the number of visible spins. Yeah. And the way they did this was basically very straightforward, very variational approach. So they basically used the energy to define the cost function, and then they just minimized the energy. So in that sense, this was more an optimization problem, not so much machine learning in the sense of inferring the model parameters from data, yeah, from actual input data. But then this, of course, changed when people then started to apply this to tomography. And then the first thing to do was then, of course, to restrict to pure state tomography, because pure states in the end is what we can nicely and efficiently describe by the RBMs. Only that now it's much closer to the original spirit of machine learning, because now we can actually really talk about training data, because we now assume that we have a, so to speak, expectation values for certain party measurements, and then now we want our model, ansatz wave function, to match these probabilities. Yeah. And for the cost function now, I mean, now we want to, so to speak, approximate the actual probability, the probability distribution giving rise to the expectation values of the measurements. Due to the actual state, we want to approximate by the neural network state, and then we need, as it, so to speak, to define the cost function to get distance measure in the space of probability distributions, so to speak. What people have been using is the Kullback-Leibler divergence, which is basically a distance measure between probability distributions. And now what they showed then in 2018 in the Nature Physics paper was that this program can be performed successfully, actually very successfully, and they can reliably reproduce the quantum state, and that was also an important result with a substantially reduced number of measurements. Yeah, and to demonstrate it, they again looked into W states, and they reproduced them for up to 20 qubits with very high fidelity. So this was very encouraging. And soon after, so same year, almost the same authors, Tola and Melko, then generalized this to mixed state tomography. Yeah. Now the idea they pursued back then was by generalizing, so to speak, the RBM model or approach of thinking, by just adding a second layer of hidden spins, which now is interpreted as the environment, describing the environment. And then, as we know from open system theory, of course, system and environment together again can be conceived as a pure state, and then we can, so to speak, again take the neural network ansatz, pure state neural network ansatz for the total system. We trace out the environment, and then we get, so to speak, the reduced mixed state of the system alone, and then we can do the training. We can train, so to speak, this mixed state, and we have to train all the weights of the system and the environment connections. Yeah.
Clemens?
Yes?
Sorry, we have a question from Sarika.
Yes?
Yeah, I raised the hand actually a few minutes back when you was in the previous slide. So can you please go back to your previous slide?
Yes, of course.
Yeah, so here, I want to understand. So you have this input data is your density measurements, and then you want to minimize the cost function, correct? And then what is your output? What output you are looking for using this neural network method?
The RBM, yeah. The RBM always produces samples according to a probability distribution. So
yes,
what the RBM can do very well is it can predict expectation values of observables, so to speak. Yeah, like you can think of it like it produces the outcomes of an experiment. Yeah, in each run you get a prediction, and then you take many samples. You get you get an expectation value of an observable, and then you just require that those expectation values, so to speak, match with the ones that you actually measured or the ones that you use to train the network. That's what you effectively want to achieve in the training process. Yeah, and that's how you formulate your cost function. Yeah.
Yeah. Okay. Thank you.
Now, here we have, because we trace over the environment, the problem here with this ansatz is that if we want to do the training here, in principle, we need to know the partition function, yeah, and this makes it very inefficient, or at least that's my understanding, yeah, and but as a fact, actually, in their paper back then, they only applied this method to a very small toy model, which was a 2-qubit system, yeah, and the suspicion is that this is because it's just very hard to scale this to larger system sizes. And therefore, for us, then this was the starting point, just to ask, okay, now we have these contrasting results, like the pure state, the tomography works very well for pure states, but is somewhat cumbersome for mixed states. So can we maybe somehow leverage the pure state tomography to do full-fledged mixed state tomography? So, and this is now where, so to speak, our own work sets in. So, and as the title already reveals, like our basic idea is that we step by step extract the eigenstates of the actual mixed state. So to understand this better, let's think of our mixed state that we want to find out as a mixture of pure states. Is eigenstates psi I with corresponding eigenvalues, and the eigenvalues, we assume they are ordered. And then we have, so to speak, one largest eigenvalue, which we call the dominant eigenvalue, and the corresponding dominant eigenstate. And usually, I mean, in the quantum experiments these days, in particular, if they strive towards some technologies, yeah, usually we can assume that the goal is always to produce an as pure as possible quantum state. So in that sense, it's usually fair to assume that the actual mixed state produced in the experiment has a dominant eigenstate with a large eigenvalue, and all the other eigenvalues should be suppressed. Yeah. So we implicitly and explicitly we have in our program we make this dominant eigenstate assumption. Yeah. And now, but because we're doing tomography, we don't know the rho. We only have measurements. Yeah. And or expectation values of measurements. Now, how can we, so to speak, extract the dominant eigenstate from the measurements? Now, the basic insight now is that the crucial question is, can we formulate a cost function which, so to speak, delivers us the dominant eigenstate as the result, as the optimization, yeah? And then the affirmative answer, of course, is that this is possible. For example, because one can prove or show that the trace distance, for example, is minimized. The trace distance is minimized between the actual density matrix and the dominant and its dominant eigenstate. Yeah, if we run, so to speak, over all possible pure states, then the closest pure state is the dominant eigenstate. And also importantly, this minimization by the dominant eigenstate is not like just a peculiar fact about the trace distance. It holds throughout other distance measures as well, like the fidelity. We emphasize this because, of course, we cannot determine the actual trace distance because we don't know the actual rho. We only have a collection of expectation values. So the best we can do is we can use an estimation of the trace distance, an estimation deduced from the measurements, and therefore this robustness, so to speak, supports the idea that this can be done reliably. Okay, and then this suggests the following iterative algorithm or approach towards step-by-step extracting the eigenvalues. So in the first step, we use, now we assume we have projectors PM, we know the expectation values the measurement outcomes according to these projectors. Now, based on these measurement outcomes, now we use the pure state tomography with the trace distance cost function or approximation to retrieve the dominant eigenstate. In the previous slide, we have argued that this is possible. And then for this, I mean, then we know the dominant eigenstate or its approximation. The head stands for the approximation. From this, we can then just calculate the corresponding expectation values corresponding to our projectors. Yeah, that's the step 2. Then in the third step, we then use knowledge. We first have to estimate the dominant eigenvalue. Now, how this can be done, I will explain in a minute. But now let's assume we have an estimate of the dominant eigenvalue. Then we can infer, so to speak, a modified quantum state, which, sloppily speaking, is the original quantum state subtracted by the dominant eigenstate contribution. But of course, we neither know rho nor rho prime. But from this expression, we can, so to speak, infer a new set of measurement data, so to speak, a deduced set of measurement data that's derived from the original measurement data and the ones inferred from our eigenstate estimation and the eigenvalue estimation. And then, based on this new set of measurement data, which is now, so to speak, the measurement data minus the contribution of the dominant eigenstate, we can return to step 1 and start over again and again extract the dominant eigenstate and so on. And in principle, this way we can step by step extract the eigenstates of the original of our original unknown quantum state until up to a desired range.
Clemens, we
Yes.
have a question from Jungyan.
Yes.
Go ahead, Jungyan.
Yeah, can you hear me? Hi, Clemens.
Yes. I hear
So
you.
in the previous slide, so I think you mentioned briefly, I mean, because we don't know what's the original state, rho, right?
Yes.
But how do you do tomography based on unknown information? Can you explain this again?
I mean, in tomography, the idea is we have a lot of measurement data for example, for many Pauli measurements, or here we talk more abstractly about many independent projectors, yeah? We just assume that the measurement data that we have accumulated is sufficient to single out a unique quantum state, yeah? So there's no ambiguity in principle left, yeah? And now,
then you mean in the step 3, rho prime is sort of new construction based on measurement you perform, right?
yes, I mean, we don't know rho prime. We don't know rho and we don't know rho prime. We only know we have an estimation of the dominant eigenstate and we have an estimation of the dominant eigenvalue. How this can be achieved, I will mention on the next slide. But just from knowing the dominant eigenstate and an estimation of the dominant eigenvalue, we can, so to speak, even without knowing rho prime, we can deduce the, we can predict the expectation values of rho prime with respect to our projectors, yeah. So this trace PM rho prime, that's the expectation value of our, so to speak, fictitious state rho prime with respect to the projector PM.
Yes.
And this we can predict because we know our original measurement data, that's our starting point, and we know we have the estimation of the dominant eigenstate and the estimation of the dominant eigenvalue. So we can calculate the right-hand side from this information.
I see. Yeah. Thank you.
And then we have a new set of fictitious measurement data, so to speak, which then can be used to extract the next to leading eigenvector. Yeah, that's the idea.
Clemens, we have another question from Igor.
Yes,
sorry,
of
Igor.
course, yeah.
So related to the previous question, I'm a bit confused about the step 3 about this rho prime, because I look at this first formula. So it's rho minus P1 and projector. So rho prime now it's not a density matrix anymore, right? It doesn't have trace 1. Then how you can work with it as before with the initial rho that has trace 1?
Yes, that's a very good point. Yeah, I mean, and of course we had to take care of that. You're correct. The rho prime itself, it doesn't look like a well-defined quantum state, but actually we don't have to worry so much about the rho prime, because the only thing we have to worry about actually is that our new set of measurement data remains consistent. Basically, these are meant to describe probabilities, and therefore they have to be positive. Yeah, that's the main constraint that we have, and that's what we take care of. Yeah, I mean, because we actually never really use this rho prime. Yeah, we don't have to worry about it too much. But of course, we normalize it this by dividing by this 1 minus the dominant eigenvalue. Basically, we renormalize it. Yeah, but of course, this is only correct if if all the estimations were exact. Yeah, I mean, in particular, you can easily see if, for example, P1 is slightly overestimated, we would get the rho prime, which has negative eigenvalues. Yeah. But this is not our primary concern, because we only have to be concerned about reproducing a consistent set of new measurement data. Yeah, and that's what I will explain on the next slide, how we do this. I mean, the idea is very simple and straightforward.
I see. Thank you. Maybe I have another question, which is maybe too general, but overall, why construct a different approach for mixed states? Why not just take this restricted Boltzmann machine in some basis for density matrices and Gell-Mann basis, and do the same exact procedures for pure states?
I'm not 100% sure if I understand your question correctly. I mean, there was this one approach with the purification where we, so to speak, artificially add a hidden layer, which we think of as an environment that we trace over. And then, of course, on the system level, we also have mixed states, but on the level of system plus environment, we have a pure state. And for the pure states, we know how to describe them with the neural network ansatz. Yeah.
But for me, it's not even clear, yeah, why they did this additional construction. So as I understand, the whole goal of this tomography in this context is to train or to optimize some Boltzmann machine. So for corresponding inputs, it gives something values that are very close to corresponding elements of a wave function for pure states. Right?
Yeah, I mean, it so to speak, it mimics the predictions of pure quantum states. Yeah.
But then
we can reproduce, for example, expectation values with respect to observables by sampling from the restricted Boltzmann machine. Yeah.
Yes, but then it's not very clear why this exactly same approach cannot be used just directly for density matrices. So let's say I vectorize density matrix. So I write it in some basis. And again, I just say, okay, my whole restricted Boltzmann machine will try to mimic this density matrix as a function. And again, I can reproduce observables and such from it. So why any additional treatment at all is required?
Well, the nice thing about the pure state neural network ansatz for pure states is that you know for sure that you, by the way you define it, you know that you describe a well-defined quantum state. Yeah, just the way you define it, how you connect, so to speak, to a restricted Boltzmann machine with the wave function, you know that you will, so to speak, get a proper, well-defined quantum description. Yeah. Now, in the case of density matrices, this is much less obvious how to do, I would say.
Well, it's one way is just to write, as you did for two speeds before, to write it as an identity matrix plus decomposition and corresponding Gell-Mann basis of required size.
You mean the block representation, or?
Kind of, yes.
Yes.
For
okay,
example.
yeah. I think the problem is this kind of representation works very nicely for single qubit, because the block sphere has a very simple geometric structure. But if you go to higher dimensional Hilbert spaces, the geometry of the space of admissible quantum states gets much more complex, and it's very hard, so to speak, to single out well-defined quantum states from ill-defined quantum states.
I see. Thank you.
But you don't have this. I mean, in the Bloch sphere picture, you have the simple argument: as long as the Bloch vector, the length of the Bloch vector is smaller or equal to 1, you have a well-defined quantum state. Yeah, that's a very simple, straightforward geometric characterization of the set of admissible physical quantum states. But if you want to generalize this program to high dimensional Hilbert spaces, I think this very rapidly gets very complicated. I think there's a book on this, which I don't remember the title of, but which basically talks about these issues. Yeah.
I see. Thank you.
Okay, sorry, I just asked a very brief question, it's Victor. You already explained in these two previous discussions. When you are talking about going from step 3 to step 4 back, so it means that you estimate P1 just in 3 steps, exactly. And when you go back, you already are measuring P2, estimating P2, and then you want to reproduce the weights of all pure states. Am I right or not?
I'm not sure if I understand you correctly.
What is the procedure?
I mean, so the PM, the M index, the M index basically just runs over all different observables that we have measured. Yeah. So in every iterative, so going through the iteration, in every step, run through the iteration, we use all the PMs, so to speak. Yeah.
No, sorry, I didn't mean the P capital. I meant the P small, which is on the previous. It's your weight. So, are you estimating the weight of the most probable of all of the pure states? Exactly.
Yes.
Here.
I mean, the P1 is the dominant eigenvalue, so to speak. The one which is ideally close to 1, and all the others are close to 0. I mean, in the ideal case, if the experiment would be perfectly isolated and perfect, everything perfect, yeah, then the produced state would be a pure state, and the dominant eigenvalue would be 1, and all the others would be vanishing. Yeah, but this is of course unrealistic.
But your procedure estimates these numbers. Do you estimate only the largest one, P1, or all of them? This is the question.
This iterative approach in principle allows to retrieve all eigenstates and all eigenvalues. But again, this is caused, like ideally speaking, because then also doing this, you also run into difficulties and it gets inaccurate. Yeah.
Okay, thank you very much.
And we will see this when we discuss a real world example. Yeah.
Okay.
The important message is that the dominant eigenvalue, eigenvector of eigenstate pair usually can be retrieved very reliably, and that's they usually carry the most important information. Okay, now let me briefly discuss how we can estimate the dominant eigenvalue. Now, as I already mentioned, one of the constraints that we make to make sure that they are satisfied is that the measurement probabilities, so to speak, by definition have to be, because they describe probabilities, they have to be larger than 0. Yeah. So this basically gives us a constraint on how we can choose the dominant eigenvalue, and we just reshape this into a definition of the dominant eigenvalue. Yeah. So we define the dominant eigenvalue basically as the value which brings this quantity closest to 0. Yeah. And then we know for sure that by construction, then, I mean, not so much the rho prime has to be well defined, but more our constructed set of new measurements is then by construction well defined. Yeah, and we can be sure that in the next step we again can retrieve a well defined. We can still assume that there's a well defined quantum state underlying these measurements, yeah, constructed measurements. And now this ansatz of defining the dominant eigenvalue, it has, of course, important properties, such as if the eigenstate estimation is exact, and if there exists a projector which, so to speak, is identical to the eigenstate, to the dominant eigenstate. In that case, also the dominant eigenvalue is estimated exactly. And also, if the eigenstate approximation is exact, then we know for sure that the dominant eigenvalue estimation can only be larger than the real dominant eigenvalue. But on the other hand, if the dominant eigenstate estimation differs from the actual dominant eigenstate, then we also can underestimate the actual dominant eigenvalue, and this then actually can cause problems, as we will see here. Okay, now before I apply to real-world data, a few last words on how we have to adopt, so to speak, the pure state tomography scheme to this iterative extraction method. Because now, I mean, what we want is we want to use we want to exploit the characteristic differences between the mixed state and the dominant eigenstates as much as possible by defining, by choosing, so to speak, or picking the best cost function. That what we find is that not the Kullback-Leibler divergence gives the best results, but actually what we call the L1.5 cost function based on the L1.5 norm. Yeah, because the dominant eigenstate exhibits characteristic statistical differences from the actual mixed state, for example, such as consistently reduced entropies, measurement entropies, or like also what we see here is that it tends to accentuate like measurement outcomes at the extremes. Yeah, and these differences are better kind of carved out by this choice of cost function. But this is just details now. Okay, now finally, of course, we wanted to apply this iterative scheme to actual real-world data, and for that we again used this trapped ions data back from 2005 with the 4 to 8 trapped ion qubits, because they actually, the nice thing is they provided the entire amount of measurement data they put online. So it's freely available online, and we used this raw data, so to speak, to test our method. And as I mentioned, what they did back then is they tried to produce W states as good as possible, and they performed all possible Pauli measurements. Yeah? but for our extraction scheme, then we only picked, so to speak, a random choice out of these Pauli measurements according to this compressed sensing paradigm, which basically tells us that a reduced fraction, random fraction of the measurements already suffices to single out the underlying quantum state. Now this table summarizes our results. The first and most important message that we get, I mean, we know here we know the exact quantum states from the tomography, yeah, we know the rows, so we also know the exact eigenvalues and the exact eigenstates, and then we can test, evaluate the fidelity of our eigenvalue approximation from our extraction scheme. Sorry, that's the eigenstate approximation with the actual eigenstate, and we find that this works very well, yeah, and very consistently. We get double 9-digit fidelity from 4 to 8 qubits. And this is even so, even though the actual eigenvalue, now these are the real eigenvalues of the actual states, they decrease, yeah. So for the 4 qubits, the dominant eigenvalue is still 0.86, and then it drops down to 0.75 for 8 qubits. Now our eigenvalue estimations, there it's a little bit more mixed message. They show deteriorating behavior. So I mean, the estimate of the dominant eigenvalues gets worse with increasing Hilbert space dimension. And also we find that the estimates underestimate the actual dominant eigenvalues, which basically hints at that even the slight deviations between the estimated eigenstate and the actual eigenstate already play a substantial role here. Yeah? But even so, if we look at the overall fidelity of our estimation with respect to the actual state, then we find that it still performs quite well and competitive. Like, for example, in the 8-qubit state, we still get like a 0.92 relative fidelity with respect to the actual state. And this has to be is to be compared, for example, to the compressed sensing result, where they get like only a slightly better fidelity by doing a low rank approximation, rank 3 approximation of the same experimental data. But now maybe the important take-home message here is now here this right part, which basically tells us that we get a very good, in summary, basically the combination of the dominant eigenstate and the dominant eigenvalue very nicely approximates, gives us basically almost all the relevant information about the actual quantum state. As since, for example, if you look at the n equals to 4 case, we see that the fidelity of the dominant eigenstate with the W state is very close to 1, and the corresponding dominant eigenvalue 0.86. If we multiply those two values, we basically get the fidelity of our target state with the actual state. So basically, we learn that instead of looking at the fidelity of the produced state with respect to the target state, we can just as well look at the dominant eigenstate and eigenvalue pair, which gives us the same information. Okay, now a very brief summary. The way I see it, the appealing aspect about this scheme is that it basically produces it extracts the relevant information about the experimentally produced state, which is like the eigenstates or dominant eigenstate and dominant eigenvalue, or let's assume also like maybe up to the rank, second or third rank, or as far as you want to go, or as far as you can go, depending on the measurement data. And of course, there's also like a benefit in the cost scaling, which is the same for all low rank approximations, because in the full-fledged tomography, usually the scales n squared with the Hilbert space dimension, but in the low-rank approximation, we have this linear scaling if R denotes the rank that we want to go down to. And also, we don't have to fix the rank a priori. We can, so to speak, stop at any point in the iterative procedure. Now, the biggest challenge is the deteriorating eigenvalue estimation, but here we think we have ideas how we can improve that. For example, if we very easily this could be resolved, I think, with an adaptive measurement scheme where after knowing the dominant eigenstate, so to speak, if we can adaptively modify our measurements, our projectors, then I think we could significantly improve also the estimation of the eigenvalues. Okay, now very briefly, before I come to the conclusions, I just wanted to mention to you a few recent interesting developments now that are happening currently. One is, for example, now also using this neural network ansatz to actually do quantum dynamics. Yeah, this has been done in the original paper by Carleo and Troyer already in the science paper from 2017, where they basically also use a variational ansatz, a variational method to do time evolution of a unitary time evolution of closed systems. And now recently, this idea has also been generalized to open system dynamics. Yeah? And also people are moving beyond the RBM, the restricted Boltzmann machine ansatz. They are realizing also that you can use other neural network ansatzes like convolutional neural networks, for example, to describe the quantum states. Yeah. And another recent development is also like, which is interesting from a different perspective, is like that now people are start to think about using unsupervised learning. So we don't, in physics applications, for example, to find topological phases or without knowledge of labeled training data. Yeah. So there's two outlooks. And now in the last slide, just a quick wrap up again, like conclusions. We have the eigenstate extraction that maybe has the nice features that it gives conceptually interesting information or relevant information about the quantum state. And at the same time, it's efficient because it goes only to a finite rank or low rank, and because it uses neural networks, which are also in the pure state case known to be or have been shown to be efficient. And in the end, I just think it's also this tomography business is a nice application of machine learning in the quantum physics context. So that's it. Thank you very much for your attention. Now, in the last slide, let me give credit to my collaborators. Of course, like most of the actual work was done by Abhijit Malkani, so he knows most of the details. Thank you very much for your attention.
Thanks a lot, Clemens, for this wonderful talk.
I'm sorry for being over time, just realizing now.
Mm-hmm. It's fine. So do we have any questions from the audience? We had quite a few in between, but Jungyun, go ahead.
Clemens, thank you for a nice talk. I have a question. You mentioned only state tomography in your presentation. So do you have any idea on quantum process tomography based on similar method you used?
I mean, quantum process tomography is again a different topic. I mean, I would say this is much harder to do. Yeah. So I'm not sure if people have thought about that already. I mean, certainly this neural network ansatz for quantum states probably would not apply there anymore, because you would have to find a way to describe quantum processes, like, for example, as depending on how general you want to set it up, if you want to like rephrase or a cross map in terms of neural networks. Yeah, sure to what extent this can be done in a viable way. Yeah. It's an interesting question, yeah, but I haven't thought about that, to be honest. Probably also because it's much harder, yeah. So,
okay. Igor has another question. Igor, go ahead.
Could you please return to this table?
Yes.
So I was just wondering, do I read it correctly? Is just the, how we call it, principle of first eigenstate that you calculate with this method correct, well, coincide better with the exact result than the full restored density matrix from the same approach?
Which part are you referring to now? Sorry, I'm not sure.
The green box.
Yes.
So it seems like some metric. So these two metrics of quality of prediction for just the values that I see for the first eigenstate are larger than for the whole density matrix. So I'm wondering about this.
Yes. But this is to be expected, because we can assume that the first eigenstate, I mean, this is here under in the green box, we see the fidelities with the target state, which is the W state, yeah? So rho is the actually produced state. So of course, because the experiment is not ideal, this deviates. So this deviates from 1, meaning that the actually produced state is not very close to the actual target state, yeah, in the sense of the fidelity is not very close to 1, yeah. But of course, because the dominant eigenstate, so to speak, in my understanding, is the part of the produced state that gets closest to the originally intended state to be produced, yeah, which is the target state. That's why, of course, it's natural to expect that the dominant eigenstate will have a much higher overlap with the target state. Yeah? Because it's a little bit fuzzy explanation, but I hope you get the idea. Yeah, I mean, what's happening is in the experiment, they do many steps to produce the W states, and then they measure it. Yeah, and in these states, of course, these steps towards the target state are by design meant to produce a W state. But then, of course, many things happen in between, like decoherence and so on. So the actual state that's produced will be a mixed state because of decoherence, the purity is reduced and so on. Yeah. But still, all these states that are meant to lead to the W state happened. And so probably the dominant eigenstate is the part of the produced state which, so to speak, most reliably or in some sense gets closest to the desired target state. Yeah.
I see. Thank you.
But yeah, but of course we don't. The dominant eigenstate, it's only implicitly there in the produced state. Yeah, we can only infer it from the measurement data. I mean, we don't. It's not the actual state that's produced. Yeah, I mean.
Thank you. Are there any more questions from the audience? If not, then let us thank our speaker once again.